Looks like pretty much everyone did it just perfectly fine. I believe it was problem number 9, where you wanted to replace unknown x with a 0, right? So when you take this limit, and since x approaches to 0, then you see what happens when you replace x with a 0. It turns out that this function is continuous function, doesn't have any breaks or anything. And that's why this is a legitimate step here. And when you do this, then zeros will make those pieces to go away where they present, and all remains will be 7. So that's the answer for this quiz exercise. So if you haven't done it yet, well, do it and send me. You can do some problem with number 8, for example, a very similar exercise, something around this. And today's goal is to do some more work with those limits to be able to better see what they are and how to deal with them. So it turns out that whenever a function is continuous, like an example here, then no matter what x approaches to, the limit will be always value at that point x. So whatever x is, you just replace into your function. And the first example here shows us that with a, we have an issue. Because when you start to approach to a, going kind of down from the right to the a, then your y coordinates of those points will be coming from this piece above. So they go to c, right? But if you start to approach to the same value of a on the other side, your y coordinates of those points are going to stay at the exact same level all the time. So they're going to be equal to b. And what's the limit? What is the y coordinate? Well, y coordinates will be jumping in between b and c, and that's not what we want to happen, because we don't know, are we at b or we are at c, and that's why this is not a limit case. The reason is we have a problem at point a. We have a break in our function. You can see it from the graph. And that's exactly what limits are designed to show us. And we're going to get to more details of it. But problem like 9, I would say, does not really make much sense from point of view of limits, because you just take 0 and plug it in, and that's all you really care about in here. And the same thing happens in exercise number 14, even though this is a fraction. But if I replace my x with what it approaches to, which is 1, then I'm going to end up with some nice arithmetic expression with a 2 in denominator and 5 in numerator. So that'd be my limit. So again, there is no issue happens when you plug in that number. And that's why I guess those called straightforward exercises. But the issue happens when you have the problems that follow, and I can try exercise like number 19, for example, because if you try to replace x with a 5, you're going to end up with 5 squared minus 3 times 5 and minus 10 in numerator, which is actually 0, right? And the same 0 will be in denominator. So that's the case. We also observed last time. So we divide in 25 minus 15 and minus 10, which is 0, by another 0, and that's not defined. And that's why problem number 19 needs to be done by using a little bit of algebra, because just plug numbers in is not working, because we don't want to divide by 0. This is called undetermined form. And whenever it's 0 over 0, it turns out you can always simplify. And that's the key idea that we saw last time. So to simplify this type of a fraction, I have to think of factoring this fraction. So denominator I can't factor, but I can use it as a factor of my numerator. So we'll always cancel, and that's why we factor. That's why x minus 5 should be a factor of my numerator as well as denominator when x is approaching to 5. So what be the other factor on that numerator? Well, look at what we're factoring on the top, number -10. So I need to have x, and then minus 2, actually plus 2 times -5 is giving us minus 10. So people usually check by looking at the product inside. It's minus 5x, and the outside product, which is plus 2x. Minus 5 and plus 2 give us -3x, and that's exactly what we need to get. So this means that I deserve to cancel these x minus 5s, and then we're left with something without denominator. So we're no longer going to have a problem with this 0 over 0. So there is no denominator, so we're not dividing by 0. So I can just take that x plus 2 and replace letter x with a 5, right? And we see that in this case, that 0 over 0 undetermined form ends up being 7. So point is, it can be any real number. It may not be even defined, but the point is 0 over 0 can be always simplified. And you say, Alex, how do you know it cannot be defined? Well, I guess I need to look at some more exercises, and that's the goal for today, just to take more and more of those limits and to feel that we get better and better ideas in here. So I guess the next page, I don't think I want to worry about, because it gets a little bit, I guess, more challenging here. So let me see what's in the next section, because I think they should give a good explanation of what's coming. They're talking about limits only from one side, because sometimes you don't have the other side of the function. Lots of times we encounter those examples. So let me consider this, a couple of examples from the textbook where we, I think, given very nice pictures. So let me see what they considered here. So for example, here's the picture of a piecewisely defined function. And our concern, of course, is where it breaks. And it breaks right here at point 2. So when we start to approach to this number 2 on one side, people say this is going to be a limit of this function when x approaches to 2 on the right. So people say x is getting closer to 2, and how to show that it's bigger. They put a plus. So that's a special notation. In other words, they say it approaches from the right side or from the bigger side. And when this happens, we are here, we're on this upper piece. So we're actually getting closer and closer to number 5. But x may be also approaching to the same number 2, but from the other direction. And people say that's from the left side. So x approaches to 2, but x is lower. That's why they say kind of minus. So it says approaching from the left, not from the right, from the left side. And if that happens, we will be on the other picture, isn't it? We will be on that other piece that gets closer and closer to -3. And since these two limits are not equal, it means the graph has a break, and it means that there is no limit. No limit, or people say limit of this function f of x when x approaches to number 2, in general, undefined. We don't know what it is. The reason we don't know what it is, because again, limit is concerned with y coordinates. So when you get closer to -3. But if you jump on the other side, then you get y coordinates with 5. So where are you? Are you here or there? So you're kind of jumping from 5 to -3, because when you are going from one piece, let me clean this mess I produced, to the other piece, because when you're on that side of 2, on bigger side, you're here someplace, but then you get closer to 2, and y coordinate goes down. Then again, see, your x coordinates may be jumping, get closer and closer to 2, because when 2 is a limit, you may start here, and then instead of going closer, you may go over. And then you jump again closer to 2 on the other side, and closer on the other side, because they don't tell us how x approaches to 2. It may be just jumping around as long as it's getting closer. But when x is on that side, we go on the upper piece. And if it's jumping on the other side, it's on the lower piece. Our coordinates, y coordinates, that's where a limit comes. They're not really going to the same place. So it's either here or there, here or there. So where are we? Are we above or are we below? So it's just not decided. And that's the point of the limit. So I'm looking at this picture, I see the break, Alex. Why do I need this? Idea is when you don't have a picture. So this is all being done when you don't have a picture. Because if they gave you a picture, then there is no point in all of this story, because you can see the function has a break. And the point of this finding limit is to identify where we have some issues with graph, where we have that break. So if you already see the graph, then you see where the break is. So there is no point of doing it. So the main idea of finding limits is to describe this issue that function has, that issue of the break, algebraically. So on this, Alex, maybe enough of this, I got it. So yeah, so if you don't see this break, if you don't know what the graph is, then algebraically you can find what's happening. And I guess that's the key idea of what we're trying to learn and why we actually need those limits. Because some people may say, just take number and plug it in. Yes, you can do it when function has no break. And actually, in those cases, we don't really need any of the limits. We need to study graph of function, and limits help. So it actually goes backwards. You have the actual function here, and without the graphing of it, you can just find those left and right limits and see that they're not equal. So there is a break in the graph. So this picture should be someplace after, not before. And I guess that's the key point of this ideas of the whole chapter with limits. And that's where the calculus starts. So They don't give you any pictures, but what they do is they give you the actual function. So you do everything algebraically. So next example, I think, gives another very good idea when we actually don't have a limit, and we have here the function with denominator when x minus 4 is in denominator. And notice that it means that x minus 4 is not 0 because we don't want to divide by 0. So we say that x is not equal to 4. And that's how people declare domain of the function. So in domain, we can have any numbers whatsoever, but 4, with exception of 4, because 4, if you try it for x, you're going to end up with something like 4 minus 2 divided by 4 minus 4, right? I take my function, I plug 4 in, because that's what one would do if they asked to find the limit of this function. And notice this is going to be 2 over 0, and that's the problem. Well, last time I told you that when you divide 2 by small, because we don't really take exactly a 0, we take a small number because actual x is approaching to 4. Nobody tells us that x is equal to 4 because x is not equal. So when x approaches to 4, see? So then the difference between 4 and something close to it will be small. And that means that we actually divide 2 by small, that gives us something very big. You say, why are you telling that 2 divided by small is big? Well, try to divide 2 by something very small. Let's say 1 thousandths. Well, when I do this, I can take a calculator and see that it'd be like a 2,000. It'd be a big number. I can try with scientific calculator. Remember, we use this so-called Desmos, so I can select it and just divide 2 by something like 0.0, very small number, 0, 1, 2,000. And now if I take a smaller number and put it in my denominator, let's say if I divide not by 0, 0, 1, but if I divide it by 0, 0, 0, 0, whatever, bunch of zeros. You see how huge the number become? Let's see, what is this? Well, there's 11 zeros. So this is 2 with 11 zeros. What is this, like trillions or something? So it's getting very big if your denominator is very small. And big means it actually tends to infinity. You ever see this before? Infinity, right? When we solve inequalities, for example, we say 2 to infinity intervals. So it is going to be huge, but on one side it's negative infinity, and on the other side it's positive infinity. They're not equal. So if you take limits on one side of 4, so notice that here we have x that approaches to 4 on the left side. Okay. So how do we say this? X approaches to 4, but we put this little minus. It means that we're coming from the left. They could have put just word left, but I don't think that anybody ever does it. So people just remember this. Minus means from the left side. And why is it negative infinity? Well, because denominator is going to be negative, because the number x is smaller than 4. Notice that numbers you take will be like 3, 3.5, 3.9, 3.99. These numbers, if I subtract 4 from them, will be negative. So I'm going to end up dividing the positive thing, like say 3 minus 2 or whatever it is positive, by negative. And that's why this is minus infinity. So it is big, it is infinity, but it may be positive or negative. So it turns out on the other side, when you start to approach to 4, but from the bigger side, the result will be positive. Because again, you're going to divide. This x minus 2 is still positive, so whatever you take 5 minus 2, so it's positive, but denominator is also going to be positive. So you're dividing two positives, that's why the quotient is positive, and that's the key part, because they're not equal, those two limits. One of them is positive infinity, and the other of them is negative infinity. So if limits are not equal, we say no limit. So if they say find a limit, you say no limit, because they both left and right side must approach to the same place, not to the different ones. And then it starts to make sense to show the graph. See, I was carefully hiding from you, because now you can see that at point 4, the graph of this hyperbola-like function has an issue. You see, there's no graph. There is actually so-called vertical asymptote. So whenever we have the number out of the main, usually we have the asymptote. And that's what actually those left and right limits justify. Of course, we're not going to do it every single time. We're just going to say, oh, 0 in denominator, that's it, vertical asymptote. But that's actually a reasoning why that's the vertical asymptote here. I can see also horizontal asymptote. We'll talk about it later. For now, we just look at this left and right limits. But yes, of course, and limits will identify asymptotes, and that's actually the why we need limits. So because once we figured out we have asymptote, then we'll be able to graph. How? Well, you put your asymptotes, and then you start to put the picture such a way that it approaches to this asymptotes like that and like that. So asymptotes are designed to help us in graphing, and the limits actually here to identify how to find those asymptotes. So that's the whole point of story. Of course, this is actually calculus 1 ideas. So I gave you the picture of what's going on. I'm not going to make you get into all this theoretical stuff related to it. I'll just concentrate on what we need for this class, such as plugging things in or simplifying. In fact, I will now concentrate on finding those left and right limits. Turns out it's the same pretty much procedure as we utilized to find actual limits in the previous section. It's just, maybe I can clean this mess a little bit. I'm gonna stop sharing and then share this screen again. And now it's nice and clean. So you can always see from the picture where we have issues, like in exercise 2, the issue is at point 2. So I can say the limit of this function. So we'll always say limit of what? Well, there is some kind of functions. They don't even tell us what it is, but when x approaches to 2, on the right side, and the right side means from the bigger side, right? So from here, we'll get on that line. So we'll keep getting closer to that blue point, which is actually 2, right? So limits of functions, always values of function. Value of function is y coordinate. So what happens with y when x gets to 2? So on one hand, it's on this piece that goes down, kind of, but we actually approach, so we go up towards that point. And on the other side, on the left side, we have same function, but now when x will approach to 2, but on the other side, which is going to be from the left, from negative direction, right? I say these are not negative, it's 0 to, well, that means actually from the left side of minus. So it looks like now we're on parabola, right? So we keep going up, higher, 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 and reach 4. Again, y coordinate is 4. Same? No, not the same. Means that there's no limit. They must be the same, n on the left and on the right. So conclusion is always identical. So when you have just, when x approaches to 2, in other words, when it starts jumping around this 2, then you jump from parabola to the line and they have a break. So we say there's no limit. And that's it. No limit. And we saw this right away from the picture. So we see here, no limit at 2. There's no problem. At 2, there is a limit because there's a little hole, but one side, y coordinates approach to level of 2, and from the other side to the same level of 2. So there is no problem here. So here's a limit, and it is 2. But here's again no limit, right? So from pictures, we can definitely nicely notice all that. Well, so let me get to the exercises here. Now let me try to do some of those. And the key idea is when you don't have any issues, when you can plug numbers in, it doesn't matter. It's a left limit, right limit, because if you have a limit, that's it. They both the same from the left and from the right. So like, for example, in exercise number 6, maybe I'll give you 5 for a quiz, but let's do a few problems first. I'll give number 6. This is our limit to take, and the limit we take when x approaches to number 1. And turns out for this case, it doesn't matter if it's from the left or from the right or the limit itself, because you can just plug this in just like we did in the previous section. Notice 1 times 2 minus 1 is going to be what? 1? Okay, so we found the limit. The issue is always somewhere in denominators. So we look at 10, for example. If you have a fraction, well, then you may need to watch out. And in this case, it looks like this is the case, right? Because when x goes to 2 on the left side, then the numerator is not a problem because it's not a 0, it's just going to be 4 and 4, which is 8. But in denominator, we seem to have 0, right? Because x minus 2 is actually small. Again, it's small when x approaches to 2. See, we don't say x is equal to 2, because when it's equal to 2, you get 0 in denominator, and that's no good, right? See, what are we talking about? Well, when x is 2, so you look at this fraction when x is 2. I just put 2 instead of x in this fraction. So we got the 0 in denominator, right? This is the problem. So you don't want to divide by 0. I say, Alex, I want to divide by 0. Well, you can try, but you won't be able to. Put it in the calculator. It's going to give you something like undefined. I see, but we divided last time. We just talked about in the beginning of this class about dividing by 0. We did, but we divided 0 by 0. See the difference? Here we divide 8 by 0. 8 divided by 0 is not defined. 0 divided by 0 is undefined. That's the only special case that we have, and that needs a little work. But if we have 8 over 0, it's just simply undefined. There's nothing you can do here. In fact, even if you try, if you say, Alex, I want to try, well, what can you do? You cannot factor your numerator to cancel. So there is nothing you can do. So if you have a fixed number, not 0, but some fixed like 8 or whatever, divided by 0, that's it. You have a problem. You actually have a vertical asymptote, remember? We just saw those pictures. So it's not really a problem. It's actually a good thing for graphing, but it's important to realize. So x minus 2 becomes small, but question is it small positive or negative? Because we already know that 8 is on the top. It is positive when you plug in your 2 into numerator. But in denominator, we're going to have very small number, right? But the sign is going to be if x approaches to 2 from the left side. So what is x? Well, it's less, right? It is less than 2. No, let's not hurry. Undefined is when x approaches to 2, but see, yes, I see this a minus. That's why I'm talking about this. So if you have the number which is less than 2, it's like 1 point something, 1.5, and if you take 2 and subtract from it, that'd be small negative. See, that's where the minus comes from, because the number is actually negative small, and that means that the minus will appear because we're dividing positive 8 by negative small number, and it's negative big, or minus infinity. See, with left and right limits, usually it is defined. If it just approaches to 2, if you just take, okay, limit when x approaches to 2, well, then, again, the question is open. You need to work on it, but it could be undefined, which is, as you said, in this case, and that's correct. But in some cases, see, in calculus, you can always come up with various examples that actually not come into one simple answer. And that's why the calculus books are big. See, if that'd be so simple, just straightforward, the calculus books will be like some children books, so a few pages and that's it. But no, there are always some counter examples, and those mathematicians just sit around and think, what, how can we actually find the example that everything is not working? They find some unusual function, very odd one, and here you go. And from that example, we produce advanced calculus, then we produce real analysis. They coming up with more of very odd functions and that's actually how this whole thing is going. And when you say, who needs that? Well, I guess not much use, that's correct. But higher levels of mathematics, they always dealing with very unusual functions, because they give counter examples to what we see is nice and continuous, and that makes us happy. But it's not always the case. That's the point. But again, I'm just not trying to scare you here, because my goal is not to get into this very details, but just to show you that these left limits usually and right limits exist, because again, they can always come up with counterexample when one of them does not exist. So usually, most cases, they exist. But the general limit is actually much harder to exist, because it's undefined, because indeed we cannot divide by 0, and that's what we just saw. So for this case, it's undefined, but left limit is minus infinity. Turns out the right limit is probably going to be plus infinity, just like in the example we considered in the beginning of section, and that's the idea. Well, for exercises, I never give my students such a torture, of course, because this is really something that is not that standard. So what I can do is just do another exercise, number 7, and then you can do 5. So how to do 7? Well, take 3, plug it in, and see what comes out. So you get 3 times 3 minus 9. So you get a square root extracted from what? 0. Good. This is 0. We say, oh, that's on the plus side. Well, see, we don't really care. Well, in fact, in this case, we do care, but And the exercises where you don't have any issues with denominators, like here, we don't really care. We take the number and we plug it in. So can you try to do the same thing for the quiz on exercise 5? I give you kind of similar quiz to what we had previously. Just to want you to start feeling good about using this left limit, because it looks like we're approaching from the other side. Maybe I should make it look a little bit bigger or something, right? Or maybe I'll rewrite it bigger, because I know it's hard to see. So x, I think, approaches to number 4, is right? And it approaches to number 4 on the left side. It's with a minus, or it's with a plus. I think it was a plus, actually, of the 3x squared and minus 9. So that's actually exercise number. Oops, I should take it easy with this parentheses. So it's exercise number 5, which is here. So try it for a quiz. Just tell me what is the answer for exercise number 5 before you enjoy weekend, because it's Wednesday, and next time we meet on Monday on Zoom, so you're gonna have plenty of time to relax. And for those people that did not have a chance to watch those lectures, to actually watch those lectures that you missed and maybe send me the answer. Actually, I see that pretty much everybody, just a couple of people. So, well, make sure you catch up, because so far, as I said, I put perfect grades for everyone. So just keep it up the same way. And
Question 5 is the quiz.
yes. Oh,
Okay.
yeah, that's right. On Monday, there is no class because it's a Labor Day. How could I forget that? Thank you for asking. Yeah, Monday, the college is closed. It's a holiday. It's a federal holiday. So Nazin is working. So you just need to relax. So you're going to have a long weekend. So you're going to see me on Zoom again on Wednesday, right? So it'll be a week from today. So enjoy your long weekend. Yeah, I totally forgot. I always look forward to the weekends, but somehow this time, well, I guess it's too much heat. But anyways, so just don't forget to put the answer in the chat and then relax. And yeah, everybody is doing it just perfectly fine. So I like that. And yeah, once you're done with a quiz, you can leave, or you can leave without even being done with a quiz. Just make sure you be done with it sometime over a long weekend, because I will send you a recording of this. I'm recording. I better stop this recording, I guess, and I will email it to you right after the class. Yes, a long weekend. I like that.